name's Alex Nguyen. This is Physics Lab 3, Black Hole and Orbits. Alright, so introduction. The goal of this lab was to use a computational modeling in GoScript to analyze orbital motion using Newton's law of gravitation. In part 1, we used real position data of a star to determine the mass of an unknown black hole. In part 2, we created a simulation involving a planet, a moon, a spaceship, and tested different launch velocities to achieve a stable orbit that interacted with both the planet and the moon. By the end, we determined that the black hole's mass and an optimal initial velocity for the spaceship that avoided crashes or escape. In the modeling, part 1, finding the mass of the black hole. In this first model, the star orbits around an unseen black hole located at the origin. GoScript estimates the star's velocity and acceleration based on its position changes each day. Using Newton's second law, we calculate the net force on the star with F net equals to mass of the star times acceleration. Then, assuming the black hole is the only source of gravity, we use the universal law of gravitation, which is the formula down here. And then we arranged to find the mass of the black hole, and we get this formula down here. And then the code loops through all the data points to calculate slightly different mass values, then averages them out to estimate the black hole's mass. And you can see that in the code here. So we also had declared our initial conditions, gravitational constant, star mass, delta at. Here's the formulas we used for part 1 and the code right here. Yep. Oops. Sorry, I messed up the thing. Okay, we're good. Whatever, it's fine. And this is what it looked like. Our average mass was 6,954.6 kilograms. Okay, and then for part 2 of the experiment, orbit and don't crash, we shifted to a more dynamic simulation, a 3-body system with a planet, a moon, and a spaceship. GoScript calculates the gravitational force between every pair of bodies using gravitational force. This formula right here. Sorry, it's weakness. Okay. Then it updates each object's motion using acceleration equals to F net over mass, the velocity update formula, and then the position update formula. And by adjusting the spaceship's initial velocity, you can control its path, whether it crashes, escapes, or moves into an orbit affected by both the planet and the moon. So by adjusting these values, we were able to find the balanced initial velocity that could create a stable figure 8-like trajectory influenced by both bodies. Okay. And that's seen in the code right here. We obviously had our initial conditions. We were able to achieve this pretty figure 8-like formula orbit. These were the initial speeds that I played around to find. This is our code. All the forms we had here were implemented in the code as shown. Sorry, I messed up the slides a bit. Okay, fixed it. Okay, so discussion and conclusion. By analyzing this, by analyzing the star's orbital data, we calculated the black hole's mass to be approximately 1.98 times 10 to the 34 kilograms. In the second part, we found an initial velocity for the spaceship that allowed it to maintain a complex orbit influenced by the planet and moon, which is seen here. Here's the initial vector, velocity vector. Some possible sources of error include relying on trial and error for the launch velocity, neglecting other gravitational influences, assuming that the planet and moon remain perfectly stationary. So part 1 of the additional questions. The rate of change of momentum and the net force aren't identical. That's because change in momentum over change in time is an average force over the time step, while F net represents the instantaneous force at any given moment. For additional questions, part 2, if we extended this model to include a black hole, a star, a planet, and a moon, and a spaceship, we need to calculate the gravitational forces between every object and update all their positions and velocities at each time step. In that system, the black hole's gravitational pull would clearly dominate, while the spaceship's influence would be negligible compared to the massive bodies. But in this case, this would be a three-body diagram problem, which of course we know in physics that cannot exist in a stable orbit. Thanks. That's it.